These are the notes on Charles' law, and we're also going to do the notes on Gay-Lussac's law at the same time. These notes are found in the gas law calculation notes document. We're going to just do the second part in a different video. As a reminder of our variables here, we also have our units. And now we're going to have, in this one, we're going to have two laws that have temperature in it. So we need to remember that that Kelvin conversion is degrees Celsius plus 273. Also, as a reminder, in the first video, we talked about how standard temperature is 273 Kelvin. So if our problem talks about that, then that is the value we would use. And standard pressure is 1 atm if that is referenced in our problem. All right, so now we're on to Charles' law. And Charles' law, when we talked about that the first time, that talks about our volume and temperature relationship. And they have a direct relationship, meaning that if volume goes up, temperature goes up, and if volume goes down, temperature goes down. And that could be the same thing, that if temperature goes down, volume goes down with that. And how we can show that relationship is with this equation. So V1 over T1, so volume 1 over temperature 1, is going to equal V2 over T2. And again, our temperatures need to be in Kelvin, so we need to do conversions for calculations potentially with that. And again, those little subscripts, the 1 just means that those are happening at the same time. The 2's are saying those conditions are happening at the same time. Usually your problem kind of has a natural 1 and 2, like start and end, or kind of initial and final. We just need to make sure that these two are on the same side, and the number doesn't really make a difference. So let's look at some examples. A sample of nitrogen occupies a volume of 0.25 liters. This is in liters, so that's a volume. At 298 K, that's a temperature. What volume will it occupy at 368 K? So looking at my units on volume are liters, and then my units on temperature are Kelvin. So these ones are already in Kelvin for us, so we don't have to do that conversion, but that's an indicator of that those are temperatures. And so as we're looking at this, if it helps to kind of identify those as you read the problem, or I will, once I figure out what I have, I will write down volume 1, temperature 1, volume 2, temperature 2, just to kind of make sure I get whatever is, whatever conditions go together, I make sure and match them up. And then I can find what is missing. So volume 1, I'm going to make the originals they gave me my ones. So 0.25 liters is volume 1. 298 Kelvin is temperature 1. And then volume, what volume? That's what we're looking for. Will it occupy at 368 Kelvin? And we have those values, so now we need to plug those into our equation. So 0.25 liters over 298 Kelvin is going to equal V2. That's what we're looking for. If it makes more sense and you like putting an X for your variable instead of the variable from the formula, you're welcome to do that, over 368K. And when we look at our units, we've got K's on the bottom, liters on the top, which means our volume 2 is going to need to have a unit of liters because those need to match up. If it confuses you to put the units in the problem, you can always leave those out. And now as we look at this math, volume 2 is in the top. And so we can just figure out what this value is, 0.25 divided by 9.8. Sorry, 0.25 divided by 298. And I got a really small number there, 0.000838 and then that's going to continue on. I'm going to just leave it in my calculator, and V2 over 368 equals that. How do we get V2 by itself? Well, the opposite of dividing is multiplying, so I'm going to multiply both sides by 368. And then I get my answer. So V2, I got 0.3087. I'm going to just go through 0.309, or I could also say 0.31 liters is the volume that will occupy at that temperature. And again, with our relationships, as we look at this, temperature went up, 298 up to 368, which means we would expect our volume to go up. It started at 0.25, ending at 0.31, and so we did see that volume increase. All right, if we do another one, hydrogen gas was cooled from 150 degrees Celsius to 50 degrees Celsius. Its new volume is 0.75 liters. What was the original volume? So with this one, it's asking for what was the original volume. So original means that's kind of our starting value. So this is my temperature 1. Original volume, I'm going to be looking for my V1. So T1 and V1. And then we've got T2, 50 degrees Celsius. And its new volume, so after that temperature change, this is going to be my V2. So we're going to have T2 equals 50 degrees Celsius, and V2 equals 0.75 liters. And I'll plug these values in that I know. And we're looking for V1. One thing we have to remember is that we need our temperatures to be in Kelvin. And part of that is because if we end up with negative temperatures, it causes problems. And so we have temperatures of 150 degrees Celsius. So I need to add 273 so that I get my value in Kelvin. So 100 plus 273. So 423 Kelvin is T1. And then same thing down here for my T2. So plus 273. 50 plus 273 means 323 K is my T2. And that relationship we're going to use is V1 over T1 equals V2 over T2. So I'm going to plug those in. So V1 over T1 equals V2 over T2. You don't have to memorize any of your formulas. We just have to know how to use them. So we're looking for V1 over T2 is 423. That's going to equal V2, 0.75 over 323 with that. Like in the last problem, you can do this, figure out what this number is, and then multiply both sides by 423. Another way you could do this is you could also cross multiply. So we could say V1 times 323 equals 423 times 0.75. Then I can do this multiplication, 423 times 0.75. That equals 317.25. And then that's going to equal V1 times 323. So I'm going to divide both sides by 323 to get that away from my volume variable. Those cancel. And so then when I divide by 323, I get volume 1 to be 0.98. And I'm going to just cut it off there, round there. Volume has a unit of liters. So my volume 2 was liters. That needs to match my volume 1, and that is our standard unit. So 0.98 liters is volume 1. All right. Our last law is Gay-Lussac's law, and that discusses the pressure and temperature relationship. This one is really similar to Charles' law but it's just pressure on the top instead of the volume. And so that is a direct relationship, meaning if pressure goes up, temperature is going to go up. If pressure goes down, temperature is going to go down. and that's assuming that volume stays consistent. Because we have temperature in here, we need to make sure with our temperatures that we have those in Kelvin, degrees Celsius plus 273 when we're using that formula. All right, let's do some examples. A gas with a pressure of 10 atm at 20 degrees Celsius is heated until its temperature is 50 degrees Celsius. What is the new pressure? So we're given a pressure of 10 and we're given a temperature. I'm given another temperature and it's asking for a new pressure. And so I can identify from there that this is gonna be a Gay-Lussac's law problem. Again, if you like to list out the variables, I like to list them out. I know not everyone does. P1, and then I've got pressures and temperatures. So I'm gonna go P1, T1, P2, T2, that. So a pressure of 10 atm, and when pressure is 10 atm, the temperature is 20 degrees Celsius. So those are gonna be my ones. And then I'm looking for my new pressure, so I'm looking for that. We'll make that P2, and then T2 is 50 degrees Celsius. And with these ones, we need to make sure and change those from Celsius to Kelvin. So adding 273, that makes T1 293 Kelvin. Adding 273 to 50 degrees, that makes T2 323 Kelvin. And those are the values we're going to use in our equation. So now we can pull that formula, P1 over T1 equals P2 over T2. So P1 is 10 over 293 is going to equal P2, that's what we're looking for, over 323. Again, when you're solving, if you have your variable in the denominator, then it kind of makes the most sense to cross multiply. But again, using whatever algebra skills, whatever makes the most sense. I'm gonna go cross multiply. So 10 times 323 is 3,230 equals 293 times P2. Divide both sides by 293. So 3230 divided by 293. And then we're gonna get that P2 equals, I got 11.02, I'm gonna go 11.0, and then pressure, what is the unit on pressure? Well, our standard unit is ATM. It's gonna match that pressure from before, so 11 ATM is the pressure after. All right, one last problem. Feel free to pause and then check with what I got if you are confident to do this on your own. A gas has a pressure of 0.75 ATM at 50 degrees Celsius. That's temperature. What is the new pressure at standard temperature? And standard temperature is 273. So even though it's not giving us a number, we know that that's 273 Kelvin. All right, so with this, I'm gonna just assign this is P1, this is T1, and then new pressure, that's P2, so then my new temperature is gonna be T2. Yeah. We need to make sure our temperatures, anytime we're dealing with temperature, we have to make sure they're in Kelvin. So T1 is gonna be 50 plus 273 because we need to get that to Kelvin. So that's 323 Kelvin. And I can go ahead and grab my equation with that. So we're looking for P2. So P1 over T1 equals P2 over T2. And we'll have 0.75 over, make sure you use your Kelvin, 323 is going to equal, we're looking for our new pressure, over 273 with that. To solve, I can do my 0.75 divided by 0.323. And I get a pretty small number, 0.0023, and then that continues on. And that equals P2 over 273. So the opposite of dividing is multiply, so multiply both sides by 273. This has a decimal there. And P2, now that that's by itself, P2 is equal to 0.63, and we need a unit ATM. All of these problems had us solving for something in the numerator. It is possible to have a problem where you have to solve for something in the denominator. We'll probably see some of those in the combined gas law, but just know that it is possible to solve for a temperature. Reach out to your teacher if you have any questions, and good luck.